This episode of the HVAC School Podcast is made possible by some pretty good companies, our sponsors. And those are Fieldpiece. Fieldpiece is going to be at the AHR conference. I'm going to ask you to stop by their booth at C6359 at the AHR conference, or AHR Expo, as it is properly called, in Atlanta. I'm going to be by the booth a couple different times, so if you swing by, there's a good chance I might be there. We have been trying out their new JobLink probes, the JL3 series of probes. We really like them. They are one of the best options for using MeasureQuick out there because of the tremendous range. They have listed on them, I think, 300-foot range. And as long as there aren't any maybe thick concrete block floors or something in between, you're going to get all of that with the JobLink probes. They really are great, and you can use them to have some of your air probes on the inside and your refrigerant probes on the outside and pull those all into MeasureQuick. So if you haven't looked at Fieldpiece yet, I would suggest that you do so and take a look at the products at AHR at booth C6359. Also, big thanks to Refrigeration Technologies at refrigetech.com. They're going to be at B4417, and I'm going to be at their booth on Monday at 3 p.m., so stop on by. That's Refrigeration Technologies. They make Viper cleaners and Nylog and all sorts of other things. Also, big thanks to Hvac and HvacGlobal.com. And then finally, Carrier and Carrier.com.
This is the guy who once had to have a bank evacuated because he tested the heat strips during a maintenance. Brian Orr.
Today on the podcast, hey, this is Brian. This is the podcast that helps you remember some things you might have forgotten along the way, as well as helps you remember some things you forgot to know in the first place. I know you never get sick of hearing that, so I don't want you to miss it. And today we've got Jason Obrzut on the podcast. Jason is one of the finest young educators in the country, nay, in the world, if not the universe. And he has got a lot of stuff going on, a lot of irons in the fire, but he took the time to come on the podcast and talk through furnace sequence of operation, which is always a popular one. He's got a nice little reminder phrase that you can use, and I won't give it away. Here we go. Jason Obrzut talking about furnace sequence of operation. Thanks for coming on, Jason.
Thanks for having me.
That was kind of weird. Thanks for coming on, Jason. Today we're talking about the sequence of operation for gas furnaces, which is a topic that, frankly, I stole from Zach and Andrew's podcast, HVAC Shop Talk. If you don't listen to that podcast, go over and take a listen. Jason had a great episode over there about diagnosis of smart valves, Honeywell smart valves. And he had a pretty good little, what do you call it, a ditty? Is that what it's called?
Yeah, he called it a ditty, yeah.
A ditty, okay. Yeah, Andrew's got the military jargon now. And it was good, and I thought, I don't know that I've actually done a furnace sequence of operation. I mean, I may have done one, but it's not my cup of tea. So I figured let's do it soup to nuts for a new technician, maybe who is still in school, or maybe somebody who's in a marketplace like Florida where we don't work on very many furnaces. It's good to know what to expect when you walk up to a furnace the first time.
Yeah, if you don't use it, you lose it type thing, where in the summertime you're running AC calls left and right, and then months later, the temperature drops and all of a sudden the furnaces are back on, and it's been months since you looked at a furnace. That's where it comes in handy.
All right, so before we call out the ditty and start on the step-by-step, I want to give you a chance to talk about the book real quick, where people are going to be able to find it when it is out. I don't want anybody to miss that.
Thank you. I work for ESCO as a content developer, so this is a project we did with them. The title of the book is Gas Heating, and it's an overview of everything from combustion to components to wiring diagrams, sequence of operation, installation. It's one of their longer books that they'll have published. It took a year and a half to write. We had a real good team, people looking it over, telling me, hey, you should have this or have that. Teachers have looked at it. I've taken input from technicians, students, teachers, manufacturers. I mean, it was a very long process to get it together. We're hoping that it's going to be real useful to not just students, but also teachers and technicians as well. It will be available on escogroup.org after the first of the year, I believe. We got all of the copyright, ISBN, all of that information set up, so it should be on the website very soon.
Great. So yes, ESCO's website, that's where you can find it. ESCO has put out a lot of different books over the years of an educational type books. And a lot of technicians miss out on books that are kind of designed for the classroom, but have really good information for the field. And this is going to be no exception to that. So what we're going to be talking about today is stuff that you can find in there if you want to reference it later. If you are a contractor or a service manager and you've got technicians who maybe struggle with gas furnaces, then this is going to be the book you want to get. There's a lot of great books out there, like, for example, the Rack Manual, which Jason also contributes to and is going to be on the cover of the new Rack Manual, which is pretty cool. But it's a small segment of that manual covers gas, where this kind of takes a deep dive into gas, which is what a lot of technicians need more of.
ESCO, they do a lot of that. They put out a lot of titles that are short, sweet, and to the point. It's not this 600-page volume. A lot of their titles are 1 to 200 pages, and they're primarily focused on one aspect of either a large textbook or a piece of the trade, something like that.
Yeah, which for technicians I think is good because it's a little less overwhelming. It's also going to be used in classrooms, but I think techs miss out on some of this type of content that's maybe written in books that they would not think of buying and keeping on the van. But I think this is one that you're definitely going to want to go out and get. So let's go ahead and dive into it. So let's start with, what is the ditty?
I've broken it down into, and there's a lot of subsections and little things, but there's 6 steps. And then there's a lot of filler material that goes in between the steps. But the 6 steps, I break it down to our thermostat, inducer motor, safety switch, igniter, gas valve, blower motor. So it's thermostat, inducer motor, safety switch, igniter, gas valve, blower motor. And to remember that, it's take it slow, it's going to blow.
Okay, take it slow.
It's the first letter.
Is the it's a anything, or is that just a filler?
Igniter.
Oh, igniter. Okay, all right. I couldn't write fast enough. So thermostat, inducer, take it slow, igniter, it's gonna, gas valve, blow is blower.
Right. Now, the safety switch is a generic name for the pressure switch because we in the industry can't decide on common terminology from one manufacturer to the next. It's a negative pressure switch. It's a pressure differential switch. It's a combustion vent switch. I just gave it the generic name safety switch, but that's the switch we're referring to, the pressure switch.
Yeah, I think when I first came into the trade, the guy who I rode with called it the air proving switch was the term he used for it, which is like so many different names. All right, so let's start at the top and walk through it. So you walk up to a gas furnace, you power the thing up, and we're going to walk through the steps that you expect to see happen. So we're not talking faults here initially. We're just talking what a gas furnace should do when it's working properly. And before we even do that, is this fairly universal? Does this work for really high efficiency furnaces all the way down to standard 80%, or is there some variability there?
Anything that uses a circuit board, basically. Induced draft models. It can work for high efficiency, 80%. I mean, it'll even work on the smart valve furnace. It's just that there's 2 circuit boards that are doing it instead of 1. I mean, if you can apply it to intermittent ignition, direct ignition, spark ignition, hot surface ignition, any type of ignition system, as long as it's induced draft, uses a circuit board.
So if it's using an old fan type control where it's got no inducer and very, very simple, then this wouldn't apply. I mean, it still kind of does. I mean, some of it applies, just not the whole thing.
Right, all the steps aren't there. In the standing pilots, the natural draft, as soon as you turn that thermostat on, instantly that gas valve fires up. There's nothing in between there. I mean, it's instantaneous. You put the red and the white thermostat together and the gas valve is on. There should be.
Let's start with thermostat. So we walk up to a gas furnace, obviously disconnects on. We start with the thermostat.
Right, the thermostat has to send the signal to the circuit board that we need heat. It has to initiate the call for heat with a 24-volt signal to the W terminal.
And we don't want, because this came up years ago on some Lennox furnaces that we had down here in Central Florida, you don't want a G call simultaneously. We had some thermostats that were set up for electric heat, and they were sending a G call along with a white call, and that's not desired.
No. Certain furnaces may lock out in that condition. Some will just turn the blower on instantly, and you'll be circulating cold air because the furnace hasn't had time to warm up. It may affect your venting if the blower is already on when the furnace is trying to warm up. There's quite a few issues you can have with that. I mean, when we say call for heat, gas furnaces weren't designed to have the blower energized immediately.
Right. And for those who are working on older electric fan coils where you needed to have a G call in order to bring the blower on, and even then, that's really abnormal. I mean, in most cases, you're going to have some sort of fan interlock. In general, in heat, you don't need a G call. You just go with the W call, and that's your thermostat signal. So 24-volt signal, usually using the white wire to the W terminal. And then next we have the inducer.
Right. Well, the board works on a series of inputs and outputs. For every input, there'll be an output. For every action, there'll be a reaction. So when the board sees 24 go into W, the next step is going to be a 120 signal out of the board to the inducer motor. And that's going to start the draft inducer, combustion blower, power venter, whatever you want to call it.
All right, so let's pause there real quick and let's just nail down, for techs who are really unfamiliar with furnaces, what is the point of that inducer?
On most furnaces, it's used to pull the gas, combustion air, flue gases through the heat exchangers to deposit them into the exhaust. On Category 4 furnaces, on high efficiencies, it actually pressurizes the flue pipe to aid in the venting. On your Category 1 furnaces, it just dumps the flue gases, and the temperature of the flue gas is what creates the venting action. So we needed to pull in the gas, the combustion air, to establish the fuel to air mixture in the burners, and pull the combustion gases through the serpentine heat exchangers because they won't rise through that on their own.
So in an old traditional non-induced natural vented type furnace, you were just simply relying on the free draw of air being brought in with the flame, your primary air being brought in with the flame, primary and secondary air, and then just the heat rising up the flue or chimney is what would then draw additional air in. But that was when you had a very simple type of burner design where you would look in and you would see the flames essentially going straight up, which wasn't a very efficient design from the standpoint of heat transfer. Or nowadays we have these, like you mentioned, serpentine heat exchangers where it's much more complex. And so you need to have that additional force provided to help draw that air in.
Right. The older furnaces used a straight up and down heat exchanger where the flue gases rose really fast, actually, and it would draw in a lot of the air needed. So the amount of time the flue gas spent in the heat exchanger was real low, as the flue gases just went straight up and then straight out. Whereas the modern furnaces use tubular or clamshell serpentine heat exchangers. And even in high efficiency, we add a secondary heat exchanger. The gases won't naturally walk through there and come out into the combustion or to the vent pipe. We have to kind of pull them through there.
Got it. And so a key thing here is that when we think of this inducer, and you mentioned it, we can think of it as always being positive pressure, but in the older furnaces, like the ones we see here in Florida, 80% standard efficiency furnaces, it's still going to have a negative pressure on the flue. If you were to measure it with a draft gauge, you would still see under atmospheric pressure. Whereas with the higher efficiency systems, you're going to tend to see an actual positive pressure in the venting.
Correct. Yeah. You'll see larger flue pipes on the 80%ers, and then the smaller 2-3 inch PVC on the higher efficiency. It has that effect. If you take a water hose, and you just let the water start running out, and then you take your thumb and you put it over the hose and you get this force, when you have a larger pipe like that, there's no pressure that builds up or anything like that. Whereas in the high efficiency, when we take these 2 or 3 inch pipes and squeeze it, we do get some pressure buildup.
Perfect. So that is the inducer. And then after the inducer, we're looking for safety. And we mentioned this is the word that maybe could be a little confusing. But how does that switch work?
On most models, it's a negative pressure switch. It'll have a hose connected to either the inducer housing or to the heat exchangers. And it takes that negative pressure, that suction that's created by the inducer motor and the heat exchangers to close it. So it's a normally open switch, and the negative pressure generated by the inducer will pull that switch closed. And the reason for that is if we have a block in the flue pipe or something along those lines, and we run the furnace, we're going to have some serious issues with flue gas and flames shooting out of the furnace with this motor added to it, this inducer motor. So if we do have any kind of restriction in the flue, we won't generate that negative pressure needed to close the switch. The switch will prevent the furnace from operating.
Yeah, it goes back to that way that Dave Barefoot taught me the name of the thing. He called it an air proving switch. That is kind of its job, is it's there to prove, to make sure that you have air that's able to draw through, which is not just the inducer fan, because that's what a lot of guys think. They think, well, if it's not pulling enough air through, it's got to be the inducer fan, or it's got to be the switch, maybe not making because it's not working right. But anything within that assembly in the heat exchanger or in the flue or venting that's restricting the flow of air, say you have a bird stuck in your flue pipe or whatever, that's going to cause you to not have enough air moving through. And then that safety switch is supposed to not allow it to turn on actually apply gas to it and turn on the furnace so you don't have danger.
Right. We won't make it to the next step.
Exactly. And so when we think about furnaces, we have these two things that we've got to prove. We've got to prove that you have air, because if you don't have air, you're going to have problems. And you also have to prove that you have flame, so that way you don't keep putting unspent gas into it. And those are two proving functions that we have to do before we can allow a furnace to keep operating.
One of the things that always comes up is a cracked heat exchanger. And if there is a crack in the heat exchanger, depending on the size, the pressure switch may not close. I mean, these pressure switches work on really, really low pressure, 0.5, 0.3, 0.2 inches of water column. Some can get into the 1 and 2 range, but think of it as a straw in a soda. When you put the straw in a soda and you take a drink, the soda comes up through the straw. But if you cut a hole in the side, you don't get a whole lot of soda up through the straw because you're sucking air in through the side. You've lost your suction. So depending on the size of the crack in the heat exchanger, you won't generate enough suction to pull that switch closed. There's things where we run into issues with the gasket between the inducer motor and the furnace, where we're drawing air in through the side. we don't have enough suction to close it. So there's a variety of issues that can get into why the pressure switch didn't close. Simply diagnosing it as, okay, it didn't close, it's a bad switch, is improper. You'd have to find out first why. You'd have to hook up a manometer and see, okay, what kind of suction am I looking at?
Yeah, anytime you have any safety that's not closing, I mean, if you think about it on the air conditioning side, it would be like saying, well, my thermal overload inside my compressor has failed. It's a bad thermal overload. It's like, no, something caused that problem. You always want to figure out the why behind a safety failure, because in order for it to not be closing, there's some kind of core reason that that's going on. Not to say that you can't have a failed switch, because it can happen. But I've seen it everything from, like we mentioned, an animal of some sort in the venting, to another common one that we saw for a while is cracks in the tubing. We see this a lot in gas pool heaters where we work. If you have cracks in the tubing that feed the switch, well, then that's obviously going to cause it not to make as well. And sometimes those cracks can be very hard to see visually. So a lot of little things to look for.
Another thing you get in cooler climates is a little bit of moisture, condensation in that hose in the tubing that connects the switch to the inducer or to wherever it's taking its suction from. Just 1 or 2 drops of moisture in that little hose and the switch won't close. So that's a common thing too.
All right. So step 1, thermostat. So remind me the ditty again before I forget. I'm already forgetting it.
Take it slow, it's going to blow.
Take it slow, it's going to blow. Okay, so thermostat is first. That's your W call, 24-volt W call. Now your inducer is spinning and it's moving the proper amount of air. So now your safety switch is proven that there is enough air and it closes. So what's next?
Once the switch closes, it's going to send another signal back to the board. Remember, it's input-output. 24 into W, 120 out to the inducer. The pressure switch closes, it says 24 back into the board. So the board's going to respond. It's going to send out a voltage to the igniter, whatever the igniter may be, a spark igniter or a hot surface igniter. And this is where we're going to get our first time delay. There's going to be a delay built into the board to allow the igniter, if it's hot surface, to reach temperature. We may have a 30 or a 45-second delay or a minute delay for the igniter to come on. Some of these newer furnaces, the higher efficiency, 2-stage, 96, 97%, they do a little test with the igniter. They start off with the first time you light it up, it does a 60-second warm-up time, and then each ignition sequence after that, it cuts 10 seconds off or 5 seconds off. And what it's doing is looking for the least amount of time that it can stay energized and still achieve ignition. And then once it finds that, it sticks at that.
And what's the reason for that? Is it the life of the igniter? Is it energy usage?
It goes down to the life of the igniter and then quickens up the process. If I have to wait 60 seconds for the igniter to warm up before the gas comes on versus 30, we get the burners on 30 seconds quicker.
And there's a couple different types of, I know that's not what this podcast is about, but I think it's worth calling out the most common types of igniter technology that we see now. I think most commonly would be silicon nitride. Is that right? Silicon nitride, hot surface ignition?
Yeah, there's 2 of them. You got the silicone carbide and the silicone nitride. On new models, on everything today, you'd find the silicone nitride. On all your existing models, you'll find the silicone carbide.
Right.
Those are the real fragile ones.
Right, the ones that you're always seeing cracking. The silicon nitride tends to just be like a very simple, looks like a straight up little rectangle, little stick. And the silicon carbide tends to look more almost like a coil kind of a thing.
Some of them do, yeah.
Yeah, varying designs, obviously.
Weird shapes, right?
Yeah, tend to be more so. And with silicon nitride, for a while there, and I don't know that they're still doing this, but they were using a pulse width modulated signal to the igniter in order to reduce the heat of the igniter to as low as they possibly could and still achieve ignition. It's been so long since I've messed with many of these, but
the first models did that, yeah. Now they all work on the standard voltage. But back when they came out, if you wanted to put a nitride igniter into a furnace that had a carbide igniter, there was a little adapter, a little box that you had to put in between the igniter and the board to kind of regulate the voltage to the igniter to temper it down. But today they've got it set up to where you just hook it up to the board and it's a go. There's nothing kind of in between there anymore. And they are way more durable. They don't crack nearly as often.
Yeah, it makes a lot more sense. I remember when Trane first started using silicon nitride, there was all sorts of training on that because it wasn't very easy to test because it wasn't necessarily just strictly 120 volts. Mike Procup, he was the one who I was listening to about that. He did some classes on that, and I remember it blowing my mind when I was 19 or 20, whatever.
Yeah, the original models, I believe, were working on 90 or 95 volts at sometimes different frequencies depending on who made it. And the little box that was there was, when they had settings, if you read the manual, it would say, okay, set it to A if it's a American Standard. If it's a Trane, you set it to B. If it's a Goodman, Amana, you set it to C. So they had different settings for all the different manufacturers.
I want to take a quick second and thank one of our sponsors, and specifically today, I want to thank Aeroasis. Aeroasis has been with HVAC School for a while. They make really nice indoor air quality products. Really 3 primary indoor air quality products for the air conditioning and refrigeration industry. They make the bipolar product. That's an induct air purifier, uses bipolar ionization, very easy to install, no parts to replace. A real great kind of entry-level indoor air quality product. It helps kind of bond together particles, and it deals with both living and non-living particulate matter. They also make another version of the bipolar. They call it the bipolar ice. It's easier for use on refrigeration units, specifically designed for ice machines. It can also be used in ductless, where the little brushes separate from the head unit. It really works great in restaurant applications where you have a lot of crud that wants to build up on the plates of your ice machine. It was specifically designed for that, and it especially helps deal with yeasts. And a lot of people have talked about sub shops, how the ice machines get so filthy in sub shops because of all the bread that's being handled. These greatly reduce the amount of growth on the plates. If you haven't taken a look at those, I would suggest that. And then also the Nano. The Nano is sort of their flagship product. They've made it for years. Are really well made in the USA, parts sourced in the USA, made by John Bennert is the guy who's been on the podcast, one of the owners of Aeroasis. And if you look back in the archives, look up John Bennert's name, you'll learn more about bipolar and the Nano, how they work. But they're really good products. We use them at Kalos. We don't have any warranty issues with them at all. They've been very reliable, and I would suggest that you check them out. You can do that by going to aeroasis.com/go. That's aeroasis.com/go. There's a form there. Fill it out. Let them know where you are, and they can instruct you on what the next steps are to find out more about these products in your contracting business. All right, here we go. Back to Jason. Sorry for taking everybody on a stroll down memory lane there. And then in addition to hot surface ignition, then we also have intermittent spark ignition, which will often be described as ISI, as how it'll be listed. So if it's hot surface ignition, a lot of times they'll say HSI, and ISI is intermittent spark. Would you mind just giving a quick description of the difference?
Or you could have direct spark as well.
Oh, direct spark. I'm trying to think of what uses direct spark.
Rheem.
Okay, all right.
All their residential indoor models are still direct spark. They're the only manufacturer that I know of using it on residential indoor furnaces.
So do a quick overview of the differences between those two, intermittent spark and direct spark.
All right, direct spark functions just like the hot surface igniter. We use the 10,000 volt spark to light the main burners. There's no pilot, there's no nothing. We use the flame sensor to sense that the main burners are on. Intermittent spark uses the same spark to light a pilot, and then the pilot is used to light the main burners. We see spark ignition outdoors a lot, rooftop units, gas packs, things like that, because when it comes to the wind, cold weather, things like that, obviously the older standing pilots wouldn't work, they'd blow out. And the hot surface igniters don't last as long outside when there's such a wide temperature range. It's 10 below zero out, and then you warm the igniter up to 2,500 degrees, and then it cools back down to 10 below. They don't last as long. They tend to crack a lot sooner. So spark ignition was for the longest time reserved to mostly outdoor type units, but Rheem does put them in all of their units, indoor and outdoor. So intermittent spark lights a pilot, and then the pilot lights the main burners. Direct spark uses the spark to light the burners right away. There's no pilot step.
All right, got it. So that is the igniter part. So that is the it's in the take it slow, it's going to blow. And now we get to gas valve. So once our igniter has been on, as it's hot surface, it's been on long enough, then the gas valve opens.
Right. We get 24 volts from the board to the gas valve. And this is going to initiate the flow of gas. It'll hit the spark igniter or the pilot or the hot surface igniter, and we get ignition. Now, the flame sensor is in there.
Okay, that's what I was going to ask.
Right. I mean, it's not part of the steps because the flame sensor can fall in a few different places depending on if it's intermittent ignition, where the flame sensor is picking up only the pilot flame and not the main burners, or direct ignition, where the flame sensor is picking up the main burners themselves. In intermittent ignition, the flame sensor is used to test the pilot, so the system doesn't know if the main burner is lit or not. The flame sensor is picking up the pilot flame. Now, there are some systems where you can incorporate a secondary flame sensor to pick up the main burners, but by design, in intermittent ignition, the flame sensor picks up the pilot and not the main burners.
Which that goes back all the way to old standing pilot systems where you had a thermocouple that's buried in the pilot flame. That's the old school way where you're essentially relying on the fact that if you have an open gas valve, that your pilot is going to light that primary gas that's coming through, which to me always seems a little scary. I guess you're just relying on the fact that it's going to hit that eventually.
At some time, right?
Right. At some point, it's going to cross over and hit that point, even if you had a restricted heat exchanger or something. It's just always a little scary to me. Of course, being that I haven't been doing gas for my entire career. It's less gas in general is a little bit intimidating. But you do have to have some way of proving flame, whether that flame that you're proving is the pilot or whether that flame that you're proving is the main burner. You have to use some method. And nowadays, it seems like most commonly we're using flame rectification or some form of an eye that's actually looking at the flame itself.
Right, the CAD cell.
Is there anything else that I'm missing? Are there any other common ways of proving flame?
There's a variety of different thermocouples, as you mentioned, standard thermocouple or the thermopile or the mercury fill, and then flame rectification. Those are the main ones besides the eye that we use a lot in oil.
Yeah, is the eye used in anything else commonly? I'm trying to think. I don't know that I've ever seen it.
Not residentially.
Yeah, I've run into it a few times in, like you said, larger stuff, commercial, but not residentially. Okay, and then it's time for the blower. And so the blower hasn't been on this entire time. It's been off because, again, we don't have a G-call. It's waiting for the furnace board to the integrated circuit board to tell it that it's time for it to come on.
Right. Once we get 24 to the gas valve, a timer is started, 30 seconds, 60 seconds, whatever it happens to be, for the furnace to warm up. And after that timer is expired, the blower motor will come on. 120 out.
Which is interesting because you had the old fan limit controls that would actually bring the blower on based on temperature, which we don't do anymore, right? I mean, that's kind of a funny thing because in some ways that almost seems like a better way of doing it. But nowadays we're always just using a timer.
It is, in my opinion. But to their credit, they have made it with dip switches on the circuit board adjustable so that technicians can go on and set the delay for the blower to come on and then the delay after the blower has turned off. We can't leave the blower on too long after the heat is turned off or we're going to start circulating cold air and initiate a call for heat again. So they put dip switches on the board so you can adjust, okay, wait 15, 34, whatever, how many seconds you want it to wait before the blower turns on. And then once the blower turns off, there's a set of dip switches for you to say, all right, how long does it have to stay on to cool the furnace down?
That's one thing I think it's good for techs to know if they're primarily electric or heat pumps, that this blower coming on after everything else is something that you should expect. When guys see the furnace come on and, oh my gosh, why isn't my blower running? Well, there's something to know. But next thing is that if you can visually see the flame, which obviously on higher efficiency units, it's not the same as with the 80% gun burners that we're used to. But if you're working at 80% and that blower comes on, it's really good to have the blower compartment sealed. Obviously, that needs to be all closed off. And then watch those flames when that blower comes on, because that's a really good visual indication of maybe there being a problem with the heat exchanger or some other communication between space air and the burner compartment.
I can't stress that enough. If you're going to be staring at the flames, we're servicing the furnace, we have the door panels off. You have to put that door panel back on. If you see the flames moving when the blower turns on and the panel's off, you're not really checking anything. You're creating all kinds of air movement in the room where you're at, and that flame movement might be considered normal. If you really want to see the blower's effect on the flame, you have to have that door panel on.
Yeah, and you have to think about other straws that could exist as well. So if you've got a evaporator coil on top and there's an overlap and maybe there's a gap there that could be affecting the pressurization of the space right around the furnace, or even if, let's say, you have a furnace that's in a conditioned room and you've got a vent that's blowing on it. I mean, you got to think about all this stuff. Anything that could be disrupting the flame from the outside, you have to kind of eliminate all of those possibilities. But once you get all that eliminated and the panel's on nice and snug and there's no straws where somebody drilled a hole in the side of the cabinet with a unibit to run a thermostat wire through or something and didn't seal it up, once all that's all sealed, then looking at the flame for flame disruption is a valid test. In fact, I want to ask you this. Is that something you still teach?
Yes. Watching the flame's reaction to the blower motor is one of the most accurate ways, aside of having a combustion analyzer, to see if there is an effect. As you said, the air that's being circulated through the conditioned space should in no way touch or affect the combustion process and the flames themselves. So when you watch that blower turn on, you should see no difference in the flames at all.
Yeah, and obviously we're talking standard efficiency, 80% type equipment, because you don't have this luxury. Of course, also when you get to higher efficiency equipment, then we should have sealed combustion where you're bringing in all of the air from the outside anyway. It drives me crazy when I see guys put in really high-end furnaces and then still pull in their combustion air from the space. It's like one of the best advantages of having a high-efficiency furnace is the fact that you're not pulling combustion air from the space.
Right. You redefine confined space. You can throw it in a closet. There's no issues.
Yep. And in Florida, we really don't care about the efficiency standpoint because we don't run the heat enough. But from a safety standpoint, bringing in your air from the outside has a lot of additional benefits, besides the fact that now you don't have to worry about having combustion air in the summer when you don't want to have a giant hole into your attic or to the outside of the space, which can cause problems if your furnace is inside. So a lot of factors there.
Another issue is returns. You had mentioned the furnace being in a conditioned space. Well, if there's a return anywhere near where the furnace may be, the return may be pulling away all your combustion air.
Right.
So moving that pipe to the outside is a big benefit.
Right, exactly. Now you got to make sure that it's done properly, and that's a whole nother ball of wax there. Obviously, if any of that's not done right, or it's accessible to creatures that can get into it and cause additional problems, now you've got another piece of venting to worry about, which some guys don't love. But I think it's something that I think we're going to go to all across the country, not just in the northern states that have traditionally used those systems.
That does cause an issue. Not all properties, not all buildings or structures are set up to have a high efficiency flue pipe. When you come out the side of the house, there has to be X amount of feet from the end of the pipe to the nearest building or structure. And in the city, these homes are all built on top of each other. You might have 3 feet of space or 2 feet of space between the homes on both sides. So your only option is to cut out the walls and go all the way up through the roof if it's not too high. I mean, it becomes a larger job. So you're going to have all these existing structures. There's a lot in the cities where the houses are on top of one another, condos, places like that, where you don't have close access to an outside wall where there isn't some kind of obstruction or restriction on the other end of it.
Right. Yeah. Sometimes you're just limited by what is, and there's not anything you can do about it, which is a challenge.
Right. When you're doing a furnace install, the homeowner says, all right, I want a 90%. All right, I'll sell you one. You got to go there and check it out. Is there a drain? Because as we know, the high efficiencies make a lot of water. You have to have a drain nearby. Where can I vent this thing? You have to scout around and say, all right, I have to find a place to terminate this. And it's not universal. Each different manufacturer prints a chart in the install manual for how many feet of pipe, how many elbows you can use. There's a lot that goes into that. The inducer motor, how well it can pull through, and the temperature the flue gas is coming out. So it's not, oh, you got 60 feet on this. Well, some you may have 60, some you may have 80. You may have to step it up to 3-inch. Some you only have 40, depending on how many elbows. There's some calculations that need to be made. Back in the day when you were selling 80s, you just, all right, we connect it to the flue pipe and that's that. But with these, you have to bring them to the outside wall, and you're going to have to go on the site, investigate, and plan for a high efficiency install.
And obviously, when you're not going to have as easy access to see flame disruption and all that, this is where combustion analysis comes in, because it's the same sort of process, but instead of looking at the flame with your eyes, you're watching your combustion analyzer, what it is before the blower comes on and what happens to it after the blower comes on. That's a really good indication when you can't necessarily use your eyes for the diagnosis.
Right. You're watching your O2 levels, your CO2 levels rise and fall with the blower. That shouldn't happen.
Yeah. And again, just even with that, though, you got to keep in mind that there may be some tiny changes that occur just because nothing is ever perfectly sealed. So sometimes you're going to see some small changes, but you shouldn't see anything significant.
I was going to bring up one more thing. Notice that when we went through the whole sequence of operations, thermostat, inducer, motor, safety switch, igniter, gas valve, take it slow, it's going to blow. We went through all the components. You didn't hear anything about limit switch, rollout switch, any of the safety switches in that sequence of operations. There's a reason for that. In most systems, those are being monitored 24/7, whether the heat is on, whether the air is on, whether nothing is on. So they're not necessarily a part of the heating sequence. There's a constant 24 volts running through the limit switch, and sometimes the rollout switches are in series with the gas valve, and I get into that later. But when the limit opens, most boards respond the same way. They're going to turn the blower motor on, and sometimes the inducer motor, and stay that way until the limit closes. You don't get your sequence of operations. You won't start with thermostat, and it does nothing. It turns the motor on and stays that way. That's a clear sign that we have a safety issue. When you come up to a furnace and you see the blower and the inducer are running and we got nothing else going on, you probably have an open limit switch or rollout switch. They use a safety loop for that.
Right, versus maybe the old school way when we would think of a standing pilot system with the thermocouple or thermopile, where we thought of it all as a single loop that went in and out of each safety and then back to the gas valve. Nowadays, you've got this integrated circuit board that's essentially watching its own set of circuits, and it's going to throw a fault of some sort, whether it's flashing lights or a code or something on the controller and on modern communicating equipment. It's watching these circuits individually. Just like you said, you have a high limit that where the system's out on high limit, it's going to, at the very minimum, bring the blower to full speed and almost always bring on the inducer too. And it's just going to sit there flashing whatever code your high limit code is. And that's what you want to look for new technicians. If you're going to a system that has some sort of a fault in it, you don't want to walk up to the thing and immediately just start pulling panels off. You want to walk up to it and look to see if there's any existing codes or anything that the system's telling you before you start pulling it apart. Because sometimes in certain brands, you'll actually clear the codes as soon as you pull that door off and trip the door switch.
That's big. And the other thing I would say is after you've seen the code and it says, let's say, open pressure switch or overheated for whatever it happens, to shut the furnace off As long as it doesn't say the flames rolled out or something along those lines, shut it off, turn it back on, and observe it for yourself. For example, it may say flame not detected. Well, that can be a million different things. It could be that the pressure switch didn't close. It could be that the igniter was cracked. It could be the gas valve was bad. The flame sensor could have been bad. You know that a flame wasn't detected, but it doesn't necessarily point you to, okay, replace this part. There's still investigative work that needs to be done on your end. I always tell technicians when I'm teaching the troubleshooting that you need to listen to the customer. They're going to have some positive information for you, but you need to see it for yourself. You need to observe the sequence of operations for yourself and see, where does it stop? When we're troubleshooting, take it slow, it's going to blow, reset the furnace and follow it through the steps. And wherever it stops, that's where you start.
It drives me crazy whenever technicians, and maybe I gave the wrong idea there when I said that, whenever technicians think that the equipment can diagnose itself, there's almost no case in which the equipment will tell you exactly what part needs to be replaced. It's almost always going to point you in the direction.
Right, but it is helpful.
Right, it's very helpful to look up those codes before you go resetting, but it's not going to say, okay, here, replace your inducer fan or replace your igniter. It's almost never that simple.
Right. One of the tips I'll give is, back in the day, the furnace manufacturers used to make one loop of safety switches, and it would have your main limit, your rollout switches, any auxiliary limit switches in one big loop. And if any one of those switches opened, it would turn the blower on, the inducer on, and it wouldn't do anything. So if it was a rollout switch, which is a manual reset switch, the blower would stay on indefinitely until someone came out to reset it. You're talking maybe a day or two, depending on how long it takes the technician to get there. Some manufacturers decided that they didn't want the blower motor running for days on end like that, and they moved the rollout switches to the line on the gas valve. So when the 24 volts comes out of the board, it goes through the rollout switches and then to the gas valve. And what happens then is if the rollout were to trip, we'd get no gas. So it would go through 3 trials for ignition, trial 1, trial 2, trial 3, and then it would go into a hard lockout where it wouldn't do anything. So there's no blower running, but it's in lockout, nothing's happening. So you can have an open rollout switch on one furnace where it's running the blower and the inducer motor constantly, and on another furnace, the same issue, open rollout switch, and the furnace just puts itself into lockout after 3 trials for ignition, but they both have the same problem. The furnaces are behaving differently.
A huge part of furnaces or any piece of equipment is that they're all trying to accomplish ultimately the same thing, but they do it in different ways with different manufacturers. So reading through the manufacturer sequence of operation, understanding what types of safeties you have in the circuit and what the different responses are, that's something you definitely want to take the time to do. One thing we're going to do on HVAC school, I just talked to one of my techs about this, is I'm going to start going through specific pieces of equipment's installation and service manuals, not reading them verbatim, but just kind of walking through them in the podcast. So that way you can get a feeling of how different manufacturers do things. Ultimately, they're all trying to accomplish generally the same thing, because I get lost. It's been so long since I've worked on certain types of equipment. Like you mentioned, a ream furnace. I don't think I've probably worked on a Rude ream furnace in, who knows, maybe 15 years maybe. And so now I don't know exactly what to expect. But if we had a manual that we could kind of walk through, I think that'll be helpful. So we're going to do more of that.
The schematic is your best friend. It's your number one tool when you're troubleshooting a gas furnace for sequence of operations. It would show you that the rollout switches are in series with the valve and not on the safety loop, and that could cause the lockout. Understanding and following the schematic will always help you in determining the sequence of operations. On ESCOs, I did a presentation on this at the conference in Vegas, and I did a whole PowerPoint to go along with it. It's all an animated PowerPoint, and it's available for free download on ESCO's website. It walks you through the take it slow, it's going to blow, and the different steps that are in there, how to teach it and stuff. And it's on ESCO's website in the conference archive section. Anyone can download it and have it. In the 2017 archive is where they'll find that PowerPoint if they want to look for it.
Okay, great. Yeah. So look up the conference archives. You need to go to the ESCO site anyway, because you need to be looking for the new book that Jason helped to write. I'm very thankful to Jason, to ESCO, that they allowed me to come out to Vegas this year, 2019, in March to speak, which I'm excited about. It's a great conference.
I am too. Everyone, if you can be there, be there. Brian is doing a session, and it's going to be great. You need to come see him.
Well, if you're an educator, because if you're not an educator, then I don't even know how I snuck in. I must have hoodwinked some people, but
you do a lot of education, believe it or not. You do.
Well, I appreciate that. I really appreciate you taking the time to go through all this with us, Jason. It's invaluable information for technicians out there. Obviously, this is whenever we're talking about gas, especially, this is something that's for techs. We say that in our tagline. It's for techs by techs. People who have been properly trained. This is not for homeowners. This is not for people who are not properly trained and licensed to do this work. If you don't have that training, then please don't try to practice this at home. But if you do have that training, then I'm going to encourage you to always work safely and make sure that you read through manufacturer's literature when you start working on particular pieces of equipment that you're not familiar with. And then also go out and go to the ESCO website, find the new gas furnace book, and purchase that as well. So that way you'll be up to date with some of the best training out there.
I appreciate that. I do look forward to the release of the book and the industry's reception of that book. You can send me comments, feedback at jobbrzut@escogroup.org. I look forward to any feedback, positive and negative, from anyone that does go on and get this book. I appreciate it.
All right. Thank you, Jason. I'll see you soon at AHR.
All right. Yeah, I'll see you then.
Thanks for listening to the podcast. Thanks to Jason for contributing to this podcast as well as others. He's a great resource for the industry, and I really appreciate him. He's going to be at AHR. We're also going to get a chance to hang out at the Educators Conference in March. And if you have a chance to make it to either of those events, I would highly suggest it. Educators Conference is only for educators, so technicians are not allowed unless you can find some sort of sneaky way of making it there. But anyway, yeah, Jason's a good guy. If you meet him, let him know that you heard him on the podcast. Also, I want to tell you a quick story. There were two goldfish, and they were in a tank, and one goldfish looks over the other and says, "How do we drive this thing?" All right. If you haven't downloaded the HVAC School app yet, go to either Android or your iPhone store, App Store, and download that. But until next time, or I should say, we'll talk to you next time on the HVAC School podcast.
Thanks for listening to the HVAC School podcast. You can find more great HVACR education material and subscribe to our short daily tech tips by going to hvacrschool.com. If you enjoy the podcast, would you mind hopping on iTunes or the podcast app and leave us a review? We would really appreciate it. See you next week on the HVAC School podcast.